Hello, I'm John Kennedy, and I'm going to be talking today about data interpretation and representation of uncertainties, particularly with regards to the state of the climate reports produced by the WMO. The first question I'm going to pose is, what is climate monitoring? What is this thing we're doing? And I've broken this down into three separate tasks here. Each of these is linked to the others, and this isn't a complete set necessarily, but I'm going to use these to focus the presentation. So the first is the production of timely and regular assessments of the state of the climate. So the state of the climate reports that the WMO produces, that the Bulletin of the American Meteorological Society state of the climate reports and others, as well as the data sets that we use to update these reports. The second of these two tasks is putting the observed occurrences into an appropriate context. So I'll talk about the context in more detail later. And then we have communicating the results. And I'll say less about this. Other people will talk about communication, but it impinges on kind of what we think an appropriate context is, who are we communicating these results to, what do we want them to know. So these three tasks are somehow interlinked. So the first and perhaps most important context is uncertainty. So what is uncertainty? So if we measure something, the value we get is different from the truth. So I've got this pink spot here on the right hand side, and say this is the true value of something we're trying to measure. Then we make a measurement and we get the value in blue there, and the difference between these is the error. Now, unfortunately, we don't know what the error is. If we did, we could just subtract it from the measured value and get the truth. This isn't the case, sadly. But what we can do is, if we have a true value here again, we can make a measurement, but we can also then make an estimate of something which we call the uncertainty, which is a range around the measured value in which we think there's a high probability that the truth will lie. And this nomenclature is borrowed from the BIPM's Guide to the Expression of Uncertainty in Measurement. There's a link there. And they go into a lot more detail about measurement, uncertainty in general. Now, why is uncertainty important? Well, first of all, from a scientific point of view, all measurements or estimates ought to have an uncertainty. And maybe this will explain why. In climate, for example, we want to know that the changes we see are actual changes in the climate and not due to errors in the measurements. And the uncertainty can tell you that, or not, of course, if the uncertainty is very large relative to the measured value. So to give you a concrete climate example, we have this statement from the IPCC's sixth assessment report. One of their conclusions was that global surface temperature in the first 2 decades of the 21st century was 0.99, that's 0.84 to 1.10 degrees C higher than the 1850 to 1900 average. So from this, we know not only that the world has warmed, the best estimate is 0.99 degrees C, but also that it has warmed considerably, even at the lower end of that uncertainty range, from 0.84 to 1.10. And at the upper end, it's warmed even more than the best estimate. There's another reason why uncertainty is important, and this is kind of related to the other one. In that uncertainty can keep messages consistent. For example, messages in the IPCC and the State of the Climate reports, or between global and regional assessments, for example. So we know that if you calculate things in different ways, if you use different data, you'll get slightly different answers. And the uncertainty is kind of a way of understanding these differences between data sets. And in fact, it acts like oil in a machine and keeps everything smoothly running, even if the parts don't fit perfectly together. If there's a small discrepancy between the global and regional assessments, for example, we need to kind of think about the uncertainty and what that means in relation to those discrepancies. Unfortunately, uncertainty is rather difficult to assess for climate data. In engineering, it's possible often to calibrate measurements very accurately. You can compare to a reference measurement, for example, and use calibrated instruments. In climate, we can calibrate individual thermometers, and Met Services do this, but we have less control over lots of other variables that might affect the measurement or the observation. So, for example, the screen in which the thermometer is found can be affected by the airflow, the maintenance state of the screen, reflections from surrounding environment shining up through the slatted sides of the screen. The enclosure in which the screen is located can also have an effect on the measured temperature. For example, grass can grow, affecting the local environments. You might have snow on the ground, which can reflect light onto the thermometer itself if you're unlucky. And then the wider environment around the enclosure, for example, trees, buildings, paved areas that might get built close to the enclosure, and which can affect the measured temperature. And then you kind of have larger differences, for example, station site location changes in equipment from automatic to manual or vice versa. So all these things can affect the measurement and affect the uncertainty in the measurement. So that's just for a single thermometer in a single screen at a single location. But when we start to calculate area averages, we need to assess the effects of things like incomplete coverage. So it's related to station locations, the variability of the climate, the spatial correlation of the field we're trying to measure. And we also might need to take into account differences in reporting practice from one location to another. For example, some countries use a min-max thermometer and take the average of the two for a daily mean. Others take hourly averages. The time of day at which measurements are made can affect the max and min temperatures and the means, and also things like response times of the instruments. And national practices can affect whole networks, meaning that some of these uncertainties correlate over wider areas. And there are uncertainties in all these things that we would like to assess. And traditionally, the method is to assess each individual component and then combine them all. So you would assess the uncertainty in the screen related variables there, the enclosure and the environment. You would add all of these up and combine them all and get an overall estimate of the uncertainty. But this is rather a large task. So just to give one example why this is particularly difficult, and that's that we don't always know what we need to know to estimate the uncertainty. So I have an example here. This is a station taken from the Berkeley Earth website, and what it shows is the difference between the temperature data at that station and the regional average as estimated by its neighbours. So you can see that they've split this up into segments, each of which is marked by a red line, separated from the others by a vertical grey line. And these red segments are individually judged to be, in some sense, individually homogeneous. So the implication is that between these red segments, there's a station move or an instrumentation change or something like that. Now, in this case, each of these changes was detected statistically. There was no metadata available to indicate that some change had occurred. So these have to be inferred statistically, and of course that comes with uncertainty. And you can see maybe between 1975 and 1990 there in one of the longer homogeneous segments, there are perhaps some shorter periods of inhomogeneities that weren't detected by the statistical method. So if we had metadata about all the station moves and instrumentation changes, maybe we would be able to detect and correct for more of the variability that we see. Unfortunately, we don't always know this, so there's a large component of the uncertainty for some of these individual aspects that it's very hard for us to assess. Now, despite these difficulties, the current global temperature data sets that we use for the global state of the climate each have individual assessments of uncertainty. So I'm talking about HADCRU-T, the NOAA Global Temp, GISS Temp and Berkeley Earth data sets, not so much about the reanalyses at the moment. And each of these individual assessments is useful because it kind of gives some indication of where uncertainty comes from, where are the uncertain areas, and this can help to improve data sets, for example, via targeted digitization. So up at the top there, you can see, a glaring example is up at the top left. This is an area average for the region from 90 south to 60 degrees south, so covering Antarctica. And you can see that prior to the 1950s, the uncertainty there, as indicated by the grey shaded region for the HADCRU-T dataset, is very large. And that's because there's no systematic observations on the continents prior to 1958 or thereabouts. So if some observations were available, that might help to reduce the uncertainty. I mean, you can see also that the uncertainty is larger as you go further back in time. So digitization of early observations is always going to be a helpful thing. Now, unfortunately, these individual uncertainty assessments aren't complete. You can't quantify all of the uncertainties. And indeed, some of them aren't accessible via these methods. There's a component like structural uncertainty, which reflects differences in the way that data sets are created. And this you can only assess by comparing individual data sets with each other. And I'll come back to that shortly. The other thing to note is that it's very hard to validate these individual assessments. Ideally, you would compare to a reference data set, a high quality reference data set, and we don't have a high quality reference data set for global temperature. These data sets are effectively our high quality reference data sets. So there's a kind of a difficulty there as well. That's very difficult to overcome. So I'm going to talk a little bit about one of these individual assessments. That's the HADCRU-T5 uncertainty assessment. Now, HADCRU-T5 is presented as an ensemble. So rather than just having a single data set, we have 200 data sets. And the spread of those data sets for any particular derived quantity gives you an idea of the uncertainty in that derived quantity. So analysis can be run on each ensemble member, and the spread of those results indicates the uncertainty. So for example, we can calculate, as we have here, time series for different regional averages, and we do that 200 times for the different ensemble members, and then we look at the mean and the spread of those estimates. Now, as I said, these individual uncertainty assessments aren't complete. In this case, an uncertainty associated with large-scale data gaps isn't included in the ensemble. So I mean, the clearest example here is Antarctica before the 1960s. There are no systematic measurements over the continent, so we can't get a reconstruction there, and that uncertainty is estimated separately for time series and for global averages. Now, I'm going to focus on one particular aspect of the uncertainty calculation, and that's the uncertainty in the infilling. So some kind of infilling is applied to the HADCRU-T data, and this is based on something called Gaussian process regression. And in a Gaussian process regression, we assume that the covariance between any 2 points on the Earth's surface is just a function of the distance between those 2 points. So where the separation is 0, where you have 2 points that are very close together, the covariance or the correlation is high. And as those 2 points get further and further apart, the covariance goes to 0, the correlation goes to 0. And we assume a constant variance to simplify the mathematics a little bit. So what does this look like? Well, when we have no data, we have a prior estimate of the climate, and that's indicated here by this thick blue line. And the uncertainty is given by the range between those thin blue lines. Now, this isn't very interesting on its own, but what we can do is we can draw samples from this prior. So these grey lines are 3 different samples drawn from the prior distribution. And these are kind of have realistic variability. They're smoothly varying in space, because we know that anomalies are smoothly varying in space. And also they have a reasonable variance, so they're between the uncertainty bounds set by the prior. Now, this is in the press when we don't have any data. But we can add data to the prior and update that to get a posterior. So if we add these red observations, which are scattered in space, then we can update the prior. And these observations individually can have their own uncertainties, and those uncertainties can vary from place to place. Now, if we take these observations and use them to update the prior, we get a posterior, which is this dark blue line. You can see that it passes through or close to the individual observations. You can also see that the uncertainty, the thin blue lines, is smaller close to the observations and wider far away from the observations. Indeed, far away from the observations, the posterior remains close to the prior estimates, i.e. An anomaly of 0 with an uncertainty range that's still around plus or minus 1 degree or more. So far away from observations, the posterior still looks unrealistic. There's no variability far away from the observations. So what we do is we draw samples from the posterior, for example, these grey lines here, and you can see that where there are observations, the samples are constrained to be close to the observations, but far away from the observations, they vary within that kind of prior range that we specified. And this gives kind of 3 samples in this case of realistic temperature fields that are consistent with the observations and consistent with our prior information about the variability. So they are in some sense realistic. And if we draw lots and lots of samples, so in this case I've drawn 100 samples or thereabouts, you can see that where they're kind of grouped together close to the observations, we can get an estimate directly from the ensemble of what that uncertainty is. We can just look at the spread. And then far away from observations, there's a more diffuse cloud. The uncertainty is larger. And in this way, we can build up a good idea of what the uncertainty is without actually having those uncertainty bounds specifically. Now that's a very schematic example. So this is an application to the actual data for HAGRU-T5. So we're using a Gaussian process regression method that allows for observational uncertainty in the reconstruction. And the interpolated grids themselves are uncertain. And we're sampling from the posterior distribution to generate a range of data sets. So on the right-hand side here at the top, we have data from 4 years. So these are annual averages for 1877, 1942, 1958, and 2016. And these are temperature anomalies relative to 1961 to 1990 in this case. And then we have 4 ensemble members running from left to right. And if you look, say, at 1877, you can see that there are differences between the ensemble members. The size of the anomalies, the patterns of the anomalies are different in each case. And all of these are consistent with the available observations and consistent with the estimated covariance pattern in the data. And on the bottom here, we have a plot showing the 1 sigma ensemble spread for different periods. And you can see that after about 1900, so from 1910 onwards, we have realistic variability across quite large areas of the globe. Prior to that, there's kind of less of a data constraint, so the uncertainty and the ensemble spread is looking more like our prior information. So that's one aspect of the uncertainty calculation. This flowchart shows a bit more about the overall process. So we start off with a set of parameters, so 200 sets of parameters, in fact, one set for each of the ensemble members. And these parameters are used to create individually 200 versions of the sea surface temperature dataset, HAD-SST4, and 200 versions of the land dataset, CRU-10-5. So those parameters control things like the size of the bias adjustments, the location and timing of breaks in the station data associated with inhomogeneities. Those 200 different datasets are each passed to the analysis and interpolation step. We do an interpolation of the data, and then we draw samples from that interpolation, as I showed in the previous few slides. And then we combine the sea surface temperature and the land temperatures together using some sea ice data to decide how to deal with things in high latitudes. And then we combine these and produce HAGRU-T5 200 versions thereof. And these processes are described in a lot more detail in the papers shown at the bottom right of the screen here for the HAGRU-T5 and HAD-SST4 datasets. So that's, in a nutshell, how we deal with uncertainty on HAGRU-T5. However, as I said already, each of these uncertainty estimates is in some sense incomplete. So another approach we can use to estimate uncertainty is to look at a range of different estimates. So we have here 6 data sets showing temperature anomalies for WMO region 2, Asia. These are anomalies relative to 1981 to 2010 in this case. We have data from 6 data sets. They don't all cover the whole period. HAGRU-T5, NOAA Global Temp, GIS Temp, Berkeley Earth, ERA 5, and JRA 55. And you can see that there's very good agreement between the data sets in general. They both show the same trend. There's the same year-to-year variability, but there is some difference. And where we expect uncertainty to be larger, for example, in the past, around 1900 to 1940, the spread, the differences between the data sets are typically larger. Where the uncertainty is small, where we expect the uncertainty to be small in the modern period where we have plenty of data, the differences are typically smaller. Now, this is a kind of slightly different approach to estimating uncertainty, to the kind of adding up of individual components. And in particular, it it's very good at estimating uncertainties on longer timescales, where some of the kind of broad scale choices we make in dataset construction really matter. And this is the method we actually use for the global temperature in the WMO State of the Global Climate. Now, I've just talked about datasets that we do use. It's also worth mentioning datasets that we don't use. So currently the 6 datasets we use for the global assessment were shown on the previous slide. We don't use some other common datasets, for example, the NSEP reanalysis, as this is rather an old dataset now. It's been superseded by newer reanalyses such as ERA5 and JRA55 that we use. The MERA reanalysis we haven't used because it has a known bias, particularly over land in the temperatures. We don't use the JMA global temperature dataset, the station-based one, as there's no peer-reviewed publication attached to it. We don't use datasets like CRUTS because these weren't specifically designed for assessing long-term trends, and we don't use the CMAP dataset, which is often used for near real-time monitoring, as this has occasional artifacts and erroneous temperatures, which might affect our assessment of the long-term trends and rankings and things like this that we care about. Now, a final approach to looking at uncertainty in the broadest sense is consistency with other indicators. So we're looking for physical consistency between, say, temperature and ocean heat content, or ocean heat content and global sea level, or sea ice and local temperatures, things like this. So, for example, we have here global mean temperature, top left, global ocean heat content, top right, global sea level, bottom left, and Arctic sea ice extent on the bottom right. And we know that the world is warming here. The global mean temperature has increased. We know the ocean temperatures have increased also because we have independent estimates of those temperatures. Now, as the ocean warms up, we expect the water to expand, and this would cause sea level rise. And this is added to by melting glaciers and ice sheets that aren't shown here. But by looking at all these and intercomparing them, we can get an idea of a kind of a physically consistent picture of a warming world. And this builds confidence and reduces uncertainty in a kind of a broader sense, and gives us an idea of how these things all work together. And one of the best examples of this is the sea level budgets, where you kind of physically cross-check things like ocean heat content, sea level rise, the contribution of glaciers melting to the sea level rise, and so on and so forth. And that gives a very good cross-check based on physical understanding that helps to kind of give you an idea of what the underlying uncertainties are in each of these data sets and whether they're consistent with everything we see. So that's a little bit about uncertainty. So a bit more now on more general context and communicating results. So when we're interpreting these data sets, the context is really key. So I'm going to give some examples using the global mean temperature series here up at the top right hand side. So this is an image from the WMO State of the Global Climate in 2021. So temperature anomalies relative to the 1850 to 1900 pre-industrial baseline, and we have the 6 data sets all shown individually. Now, these are some of the statements we made based on this time series and other information. So, for example, we said that the past 7 years were the 7 warmest years on record. Now, this is true for all of the data sets we assessed. So it takes into account the uncertainty. It also tells us that the recent past has been exceptionally warm in terms of the long-term record. You can see this at a glance from the time series, but that's a summary in words. We can also say specifically that 2021 was between the 5th and 7th warmest year on record. So if we look at individual data sets, they all lie within that range. Borrowing from the IPCC, we can say that each decade since the 1980s has been successively warmer than the one before. You can't say that straight away based on this graph, but if we average these data, that is the case. We can focus just on 2021 and say that the anomaly was 1.11 plus or minus 0.13 degrees C above pre-industrial conditions. And here the context, the pre-industrial conditions, is coming from the Paris Agreement. So we assess temperature changes relative to pre-industrial to kind of help understand how progress continues relative to the Paris Agreement targets. So that's information based solely on the temperature graph here and the temperature data. We can also kind of start to explain some of the changes we see. So for example, we said that 2021 was cooler than recent years because of the cooling effect of La Nina events at the start and end of the year. So you can see that 2021 isn't as warm as 2020 was, or say 2015 or 2016, which were boosted by a strong El Nino. And we worked with the comms team to craft key messages, and some of these are kind of been building up over the past several years. So it's a kind of an iterative process, kind of look at what's going to be effective, but what also respects the underlying science and uncertainty in the data. Now, starting to focus down a bit more regionally, I've got here again the WMO Region 2 area average relative to 1981 to 2010 in this case, not pre-industrial. We don't use pre-industrial for regional averages because we can't do it consistently due to a lack of data in some regions. But we're using, again, the same 6 data sets updated to 2021. So you can see here there's agreement between the different data sets on long-term change. There's also very good agreement in the year-to-year variability, for example, that associated with El Nino or La Nina. You can often pick out strong El Nino events in these large-scale averages, say around 1998, and the more recent ones in 2015 and 16. But also you start to see more regional variability as well. For example, for Asia, the 2015-16 El Nino doesn't show up quite as strongly as it does in some other regions. And the anomaly for 2021 in this case was around 0.9 degrees. For the estimates I have, they kind of range between 0.78 and 1.02 degrees above the 1981 to 2010 average. Now this places 2021 between around the 3rd and 7th warmest year in the past 120 years. So certainly very warm in the context of the long-term record, but not the warmest year by any means. And that was last year across the board for this particular region. Now, a cautionary note about using anomalies, I guess. So if we say the anomaly is 0.9 degrees, and even if we give an uncertainty range, this doesn't provide much context on its own. So I just kind of, if I cover up the rest of the time series, giving the anomaly on its own without any further context is equivalent to just showing someone the one data point at the end of the time series. Unless the user, unless the reader of that information has a very good understanding of the time series, of the context, then the anomaly on its own can be quite kind of hard to interpret. And this is because the baseline is, in some sense, arbitrary. 1981 to 2010 is used by convention, but unless someone has a good understanding of what that means, it can be quite hard for them to place that in a context that they can understand. Now, when we're looking at regions, one thing we can do is we can compare one region with another and start to pick out some commonalities and some differences. So for example, here I've got the area averages for the 6 WMO regional associations. Region 1 is Africa, Region 2 is Asia, Region 3 is South America, Region 4 is North America, Region 5 is the Southwest Pacific, and then Region 6 is Europe and the Middle East. And you can see that there's been long-term warming in each of these regions. The exact rates of warming at different times has varied. The y-axis in each case aren't all exactly the same here. Just one thing to note. Also, we can see that uncertainty is larger in some regions and periods than in others. Asia and Europe have generally smaller uncertainties from 1900 to present than some other regions. In particular, kind of say Africa has larger uncertainties at the start of the 20th century and larger uncertainties currently. South America has larger uncertainties at the start of the 20th century, but is comparable to other regions currently. And you can see, for example, say over Asia, Europe, kind of a period around the 1940s where temperatures kind of were rising to that point in the 1940s, and then there's a period thereafter of cooling or slower warming. until around 1970, 1980, and then a period of more rapid warming. And you can see this also to a certain degree in North America, but this is less pronounced, say, over South America or the Southwest Pacific. So we can start to pick out some similarities, and also we might look at the effect of, say, El Nino variability, ENSO variability in these different regions and how they relate to what's going on in the tropical Pacific. Now, this is up to now we've been mostly looking at the temperature data on its own and kind of building a context from that. But another thing we can do is we can bring in information from models and from the IPCC and what we know more broadly about the climate. So this is a figure from the IPCC's 6th Assessment Report, Working Group 1 Summary for Policymakers, and it shows observed changes per degree C of global warming up at the top in the middle there. And it shows simulated changes at 1 degree of global warming. So we can start to compare what we see in the observations to what we see in models. And the models are providing some kind of expectation for what the changing climate is doing. And we can kind of compare and contrast those two. And as we go forward, you can see that for different simulated global levels of global warming, we can start to see kind of certain patterns emerging. For example, the land typically warms faster than the oceans do. Warming is higher, faster at higher latitudes, particularly over the Arctic. And so these are some of the things we can start to use to understand the changes we've already seen in the observations. Now, one thing that's often used to monitor changes in the climate is trends, and this is a diagram I made last year or the year before to look at rates of change across the different WMO regional associations. So we've compared trends here over common periods. So there's a set of coloured bars for each of the periods 1901 to 1930, 1931 to 1960, 1961 to 1990, and 1991 to 2020. The different coloured bars are showing the different WMO regional association averages, trends over these periods, and then the grey bar is showing the trends in the global average over the same periods. And you can see that trends have generally increased over time. Warming through 1961 to 1990 is higher than the previous periods, and then the warming in 1991 to 2020 is kind of higher again, particularly over, say, Europe and Asia. And the size of the coloured bar is the mean of different estimates, and the black vertical line is some kind of estimate of the uncertainty based on the spread between different data sets. So we can look at this and we can say that, some certain land areas have definitively warmed faster than the global mean, as we'd expect, given that land has typically warmed faster than the ocean. But with a graph like this, you need to be very careful. When you're looking at trends, you need to be careful that the trend is really a good representation of the data before we start to make kind of strong conclusions and inferences based on those trends. So I'll just explain a little bit more about what I mean by that. So when we think of a trend, we have this notion that it can be helpful to think of a temperature series as a combination of some kind of long-term change, which is maybe slowly varying, and then on top of that, we might have short-term variations. So in this case, I've got temperature data here for one WMO region, and I've put a smooth blue line through it. So I've used the lowest smoother in this case. And the blue line is giving us, kind of an intuitive idea that there's some kind of slow variation in this data, and then there's variability about it. So the black line kind of jumps up and down above and below that blue line. Now, this is sometimes a helpful way of thinking about the data. We can think of what's causing changes from the long-term variations. But it's important not to forget that this separation is statistical. It doesn't necessarily have a direct physical meaning. So we need to be a little careful in the interpretation. We shouldn't immediately say that long-term changes are exactly equivalent to global warming. The long-term changes can be affected by long-term internal variability in the climate as well. So here is one example of a danger of using trends. So it's common to use linear trends to kind of summarize changes in climate data. So the method I've used here is ordinary least squares. The orange line is the ordinary least square estimate of the linear trend. And I mean, it's obvious in this case that the orange line doesn't describe the data very well. There are 30-year periods here where the data, the black line, is consistently above or below the orange line. There's lots of variability in this data that's not explained by that trend. And you can see in particular that kind of in the past decade or so, the data have been consistently above the trend line. So we might not think this is a good way of representing this particular time series. Now, if we use shorter trends, individual linear trends, so these are the 30-year trends I showed in the diagram with the coloured bars. You can see that these shorter trends do give a reasonable fit to the data. It's not perfect. These red lines, which are the individual 30-year trends, don't quite match up at their endpoints, as you might intuitively expect. But they're giving a kind of a reasonable description of the data. It's not an awful fit to the data here. So we can start to maybe kind of think, okay, this is perhaps a reasonable way of looking at the data. But we have to look at the data to really start to assess that. Now, if we go to even shorter trends, then we hit a different problem. Previously, with just using one trend for the whole period, you kind of get these long-term divergences in the data where the data are very far from the trend line. We have the opposite problem if we use short trends, in that the trends kind of follow the data too closely. So the trends are very strongly affected by the year-to-year variability that might be associated with El Nino or kind of regional drivers of climate variability. And in this case, the short-term trends aren't giving a good or accurate indication of what the long-term trend might be. They're too strongly affected by the short-term variability. So there's a cautionary tale here about using short-term trends to assess what kind of the overall long-term trend might be. And the same goes even for long-term trends. We shouldn't kind of extrapolate them beyond the end of the data without great care. So another way of thinking about trends and long-term tendencies in the data is to kind of make again some kind of connection to model data. So this is again from the IPCC. This is from chapter 3. I note here that the areas don't exactly correspond to the WMO regional association, so we can't directly compare. But what we have here is, if we just focus on the left-hand side here, which is near surface air temperature, we have changes in temperature for North America, Asia, Central and South America, Australasia, Europe and North Africa, the Antarctica and Africa. We have the observations in black, and we have two sets of model runs. So we have a natural only set of model runs. This is what would have happened if there had been no anthropogenic kind of warming and no anthropogenic drivers of the climate. And you can see that the kind of the green line there, which is showing the natural model runs, has very little long-term trend. In contrast, the model runs, which include both anthropogenic and natural drivers, show long-term warming that's reasonably consistent with the data. So in some sense, these models are giving us some idea of what we think an underlying trend might meaningfully be. They're kind of taking into account all the drivers, kind of the predictable drivers, if you like, of the climate. But we can also start to compare the observations to this, and we can start to see divergences, particularly over, say, North America, where there's a warmer period there between about 1920 and 1960 or thereabouts, where the observations are warmer than the models. So again, we're kind of comparing and contrasting, where are the similarities, where are the differences, what can we learn from this comparison to inform what we say about the data. So finally, I'm mostly focused on the analysis of the time series, but it's also useful to think about kind of what's happening at a very small scale. So looking at maps here of temperature anomalies the uncertainties can be quite large at the level of individual grid cells in the data sets that we're using. So I've got maps of temperature anomalies for 2021 from 5 different data sets here. So HAGRI T5, ERA5, Berkeley Earth, NASA GISTEMP, and NOAA Global Temp. And the maps at the bottom are all in the native resolutions of those data sets. And if you compare these maps, you can see that there can be quite large local differences between them. So for example, if you look at Africa, you can contrast HAGRI T5 and ERA5, so panels C and D. You can see HAGRI T5 has an area of cooler than average temperatures, average in this case being 1981 to 2010, through Central Africa. And in contrast, ERA5 has above average temperatures, with the other data sets somewhere in between the two. So there's kind of large local uncertainties. And the way we've dealt with this in the State of the Global Climate Report this year is to use a median of those data sets to kind of get a kind of consensus about what the temperature anomaly is from those data sets that we have, and also to look at the range. And the range is going to give us some idea of the uncertainty again, as we did with the time series, so we can do with the maps. So the median and the range are shown at the top, and you can see that we're kind of limited here by the resolution of the lowest resolution data sets, HAGRI T5 and NOAA Global Temp. But we're also picking up the kind of consistent patterns of temperature anomalies across all these data sets. And we also have additional information from the range up at the top right. So you can see that the range is larger at high latitudes where we have very few data, particularly over Antarctica and the Southern Ocean, and also over some regions, for example, in Central Africa, where we see these large differences between HAGRI T5 and ERA5, relatively speaking, but also in other places too. But in some places, of course, we have very good agreements. So we need to look at common patterns across the data sets and start to understand where the spread is, so we can talk kind of in an informed way about the patterns of anomalies that we're seeing. So we're not attributing to measurement error actual changes in the climate. So I just want to leave you with some summary words. So when we're thinking about kind of communicating climate monitoring information, it's always important to consider uncertainty. So we know what we're talking about has kind of in some sense really happened. It's good to look at a range of estimates where possible to understand that uncertainty. If we're looking at and discussing trends, we should be aware of how these relate to the full time series of data that we're calculating the trends for, and those trends should then be a reasonable description of the data. We should consider context when summarizing the data, and we should definitely provide enough context for the readers to understand the numbers, the statistics that we're providing to them. So I'll leave it there. Thank you very much for your attention. Yes, thank you.